minus degree 0, and then I get just minus 8. Okay, and now I repeat the same argument. For what I have to multiply x to get 2x squared, of course, I have to multiply x by 2x. And straight away I get x times 2x, which is 2x squared, and minus 2 times 2x, which is minus 4x. And I again consider the subtraction of these two polynomials, and I immediately get 4x minus 8. Attention, the degree of this polynomial is not strictly less than the degree of this polynomial, the polynomial for which I am making the division. Therefore, I cannot stop here, I have to continue. And then, now, I ask myself, for what I have to multiply x to get 4x, of course, by 4. And I get x times 4, which is 4x, minus 2 times 4, which is minus 8. And when I consider here the subtraction of these two polynomials, immediately I get 0. What means? This means that the remainder of this division is equal to 0. Then we have that x cubed minus 8 is equal to x minus 2 times x squared plus 2x plus 4 plus 0. Therefore, I can conclude that this equality is true. Ciao. We're going to develop a general strategy for finding the roots of a polynomial. It will be based on the factor theorem, and it will involve finding the root factorization of the polynomial. Now, in order to reveal fully the structure of a polynomial, we would really like to factor it into the following form. A product of linear factors of the form x minus r, and then a final term q of x, where q is irreducible, has no roots. A general strategy for doing this is the following. First, we find a root r of the polynomial p in some names. We then use polynomial division and the factor theorem to divide p by x minus r, and we know that it will be divisible, so we'll have p equal x minus r times another polynomial, p1. p1 will be of lower degree than p. We now repeat the process. We look at p1, we find the root of p1, we take out a linear factor, and we go on until we have the root factorization. So you see that we're using so-called order reduction. At each step, the new polynomial will have degree less than the previous one. Let's illustrate this with the following example. We want to find the root factorization of a certain polynomial of degree 4. First step, we observe that p of 1 equals 0, as you can easily check. It follows that 1 is a root of p. Therefore, by the factor theorem, p will be divisible by x minus 1. Now, we can perform this long division. I will spare you the gruesome details, but here's the answer, and a certain polynomial of degree 3 is the quotient. We now proceed to study that polynomial q of degree 3. We observe that q vanishes at minus 3. That is, q of minus 3 is 0. That is, minus 3 is a root. That means that x plus 3 will divide q by the factor theorem. When we do that long division, then a certain quadratic, x squared plus 2, appears. That quadratic is clearly irreducible. It can never be 0. It has no roots. So the procedure has ended. And now we get the root factorization of p. Now, when you look at this example and the way we've solved it, surely it comes to mind to ask, but how did we find the root 1 for the polynomial p? How did we find the root minus 3 for the polynomial q? To be perfectly honest, we guessed. However, we guessed in an educated way. I will explain what I mean. Consider the following example. You have a polynomial of degree 3 and you would like to guess its roots. Well, you decide that you're feeling lucky and you try x equals 1, minus 1, 2, minus 2, 3, minus 3. That is, you plug it into p and see if you get 0. Actually, none of these give you 0. None of these values are roots. Well, you didn't guess in an educated way because it turns out we could have known a priori that the only possible rational roots of this polynomial are plus and minus 1 and plus and minus a half. Why is that? It's because of something called the rational root theorem, which I now state. Here it is. Let's suppose we have a polynomial with integer coefficients whose constant term is non-zero. It might have rational roots. Any rational root can be expressed in the form p over q, where p and q are integers and the fraction is irreducible. In that case, the theorem says the p must divide the constant term and the q must divide the leading coefficient. If you apply that statement to the example above, you will see that the q must divide 2 and the p must divide 1. That leads to 4 possibilities in all. Plus and minus 1, plus and minus a half. When you try these 4 possibilities, it turns out that exactly one of them is a root, namely x equals a half. Now, note an important fact about this theorem. This theorem does not say there will be a rational root of the polynomial. It says if there is a root, then the p over q will be such that, and so on. So it's not a guarantee that there will be a rational root. It's simply a good way to produce educated guesses. Here's an example. We want to find, we have found, actually already, that x equals a half is a root of this polynomial. How do we go on to go towards the root factorization? Well, we divide by x minus a half. After the long division, we get a certain quadratic. Can we go on? Can we factor that quadratic? No, it's irreducible. Why is it irreducible? Because its discriminant is strictly negative. Therefore, we have achieved the root factorization factorization of p, and p has exactly one root. Here's another example of a slightly different type. As usual, we want to begin by finding the first root that will give us our entry point to the procedure. What should be our guesses for that first root? By the rational root theorem, we know that any rational root p over q will be such that q has to be plus or minus 1 because the leading coefficient of our polynomial is 1, and the p has to be a divisor of 8. That produces, as you can see, 8 possibilities in all, plus and minus 1, 2, 4, 8. We try them all. 8 times we calculate p, and we discover that exactly one of these numbers is a root, namely 4. Given that 4 is a root, we divide p by x minus 4, we know it will divide evenly, and a certain quadratic polynomial then results. Is that quadratic polynomial susceptible to being factored further? Well, its discriminant is strictly positive. So yes, it has 2 roots, and therefore that quadratic polynomial will be the product of 2 linear terms, namely the 2 that you see. The root factorization of p is now complete. P has been factored down as far as it can be. A cubic polynomial can have no more than 3 roots.
Finding roots in practice, step week 3. Let us consider the first exercise. We have to find the root factorization of this polynomial. How can we do this? How can we solve this exercise? The idea is the following. We want to find the roots of this polynomial. In general, it's not so easy, but we have seen in the Francis video a good algorithm to find rational roots of a polynomial. That is, roots of the form p over q, where p and q integers. Then the rational roots of this form of this polynomial have to satisfy some conditions precisely. You have that the p has to divide the constant term of our polynomial, minus or plus 4 is the same, and the q has to divide the leading coefficient of our polynomial. Therefore, the possible candidates are the following. We have plus and minus 1 over 1, because 1 divide 4 and 1 divide 3. Then we have plus and minus 1 over 3, indeed 1 divide 4 and 3 divide 3. Then we have plus and minus 2 over 1, plus and minus 2 over 3, plus and minus 4 over 1,